In the last video, I showed you how double dabble can be used to convert a binary number to BCD, which makes it effective for essentially converting it to decimal so that I can display that onto a circuit. Okay, so how does double dabble work is the question. All right, so to answer that question, let's think about going the other way. How would we go from decimal to binary? All right, so we know about that. We divide by 2. So 178 divided by 2 gives me 89, remainder 0. 89 divided by 2 gives me 44, remainder of 1, and so forth and so on. You can go down the list, and then remember, you just read back up to figure out what the binary number is. All right, so we're going the other way. We're going to start with the binary number. So if I was going to go the opposite direction, wouldn't it make sense that I'd multiply by 2? Okay, so that's what's happening here. When I shift to the left, that's effectively multiplying by 2. So the first time I do that, I want you to notice this place right here. This place right here, whoops, I pointed to more than I wanted to. Okay, right after the shift, that's a 1 corresponding to that 1. Okay, then when I shift it again, I look at these two places, that's the 2. All right, over here, I get to the 5. All right, so you can see how it's popping off the BCD the decimal digits as I come back up this path. And if I keep going, I should end up with 178 as the final answer. So the question is, why the dabble? Okay, and so it turns out the reason I need the dabble is because if I shifted 5 over by 1 place, 5, let me write it out, 101, when I shift that over, that'd be 101, and then shifting in is another 1. That's not a BCD digit. That's too big, all right? And so what I really need to do is push that so that the decimal place carries over, okay? So in other words, what I wanted is, if I said 5 times 2, that would be 10, but 10's too big of a digit. Okay, so if I take 5 and I add 3 to it, I would get 8. All right, and then when I shift that 8 over, that 100 shows up into the tens place. All right, it's a pretty clever trick. Okay, so let's see what happens there. When I dabbled, I got, let me change the color. Let me change it to blue. When I dabbled, I got 100. Okay, and then when I shifted that over, you see that 1 appearing right here. Isn't that clever? That's the 1 in the ones place. And then this other one right here, I'll circle that in red. That other one shifted in. And so between the two, I have 1 and 1, which is 11. Okay, so I use the dabble thing to take care of places where I need that extra bit to shift over into the tens column, so that I get a valid BCD digit. Okay, so you may not follow all that, but you get the idea that you have to do a trick to keep things working so it'll expand over into the next column correctly. If you have a digit that when you multiply by 2, if you get something that's bigger than 9, you're going to have to dabble. All right, so 4 times 2 is 8. That's not bigger than 9. That's good. 5 times 2 is 10. You have to dabble to make that work. Okay, so let's keep going to finish this off. After the shift, okay, let's take a look at what we have. We have a 2 in this place and a 2 in this place. That gives us the 22. All right, we didn't need to dabble in that case because both of those registers in the ones and the tens place were less than 5. Okay, so when I shift that over, I get 4 and 4. What do you know? That's right here. Okay, with 4 and 4, I don't need to dabble. Okay, so I just shift over by 2, and I get 8, and that 1 shifted in, so that gives me the 9. So that's the next place right here. But I do need to dabble that because 8 is bigger than 5, so I dabble. And then when I do that shift, it ends up with the next stage being 178, which gives us the final answer. Okay, so it's pretty clever. I don't expect you to remember all the details, but I think it's kind of cool to see how it all plays out. It's like converting from decimal to binary in reverse with this little fix that they call the dabble. Okay. Next up, we're going to do a video that talks about, oh, this is well and good, but how would you implement this with a circuit?